This video gives an overview of the regulation of extracellular fluid volume. If humans are to maintain constant extracellular fluid volume in their day-to-day lives, extracellular fluid volume must be sensed by sensors. Stimuli from the sensors must alter signals to the kidneys to affect sodium excretion. The ultimate effect on the kidneys, therefore, would be an alteration of sodium excretion. Sodium would be retained if diminished extracellular fluid volume were detected. Sodium excretion would be enhanced if excess extracellular fluid volume were detected. To be proper, what is sensed by the sensors is not extracellular fluid volume per se, but rather effective circulating volume. Remember that effective circulating volume is that portion of the extracellular fluid volume that is in the arterial system and that is effectively perfusing tissues. Generally, states of diminished effective circulating volume are characterized by low mean arterial pressure. Low effective circulating volume will be detected by sensors or baroreceptors in the cardiac atria, pulmonary vessels, carotid sinus, and aortic arch. The sensors in the cardiac atria, pulmonary vessels, carotid sinus, and aortic arch are baroreceptors. They are specialized nerve endings that respond to stretch or the lack thereof. The sensors in the atria and pulmonary vessels respond primarily to changes in blood volume. The sensors in the carotid, sinus, and aortic arch respond predominantly to changes in blood pressure. In the case of low effective circulating volume, receptor discharge is decreased. This input from these sensors is carried to the medullary cardiovascular centers via the vagus and glossopharyngeal nerves. The juxtaglomerular apparatus is also a sensor. The juxtaglomerular apparatus has baroreceptor function. Specifically, the afferent arteriole has baroreceptor function. In the case of diminished effective circulating volume, there's less stretch of the afferent arteriole. In cases of diminished effective circulating volume, for many reasons, there is diminished sodium chloride delivery to the macula densa. This is a depiction of the juxtaglomerular apparatus. The juxtaglomerular apparatus is where the thick ascending limb of the loop of Henle comes into close contact with the afferent and efferent arterioles of its own glomerulus. The afferent arteriole and perhaps the efferent arteriole have granular cells. These are cells that secrete renin. The macula densa cells sense sodium chloride delivery. In the case of diminished effective circulating volume, there is diminished stretch of the afferent arteriole. That has baroreceptor function, as I've said, and this diminished stretch leads to enhanced renin secretion by the granular cells. In states of diminished effective circulating volume, for a variety of reasons, there's diminished sodium chloride delivery to the macula densa, and this also leads to enhanced renin secretion by the granular cells. As we will discuss later, there is also another phenomenon that leads to enhanced secretion of renin by the granular cells, and that's enhanced renal sympathetic nerve activity. So let us carry on. Decreased effective circulating volume is sensed by the sensors. Input from the sensors in the cardiac atria, pulmonary vessels, carotid sinus, and aortic arch are carried to the medullary cardiovascular center via the vagus and glossopharyngeal nerves. Signals are then sent to the kidneys, and the signals are enhanced sympathetic nerve activity and ADH secretion. As we just showed, diminished stretch of the afferent arteriole in the juxtaglomerular apparatus and decreased sodium chloride delivery to the macula densa results in enhanced renin secretion. And I think it important to point out that enhanced sympathetic nerve activity also enhances renin secretion. Therefore, there are three regulators of renin secretion: wall tension in the afferent arteriole, sodium chloride delivery to the macula densa, and renal sympathetic nerve activity. The effects on the kidneys are as follows. Enhanced sympathetic nerve activity causes constriction of the renal arterioles. This leads to diminished renal blood flow and diminished glomerular filtration rate. Therefore, the amount of sodium filtered by the glomeruli is decreased. Enhanced sympathetic nerve activity also enhances sodium reabsorption by the proximal tubules. So because of the diminished GFR, there is a diminished filtered load of sodium. What sodium is filtered is avidly reabsorbed by the proximal tubules. Sympathetic nerve activity also stimulates renin secretion, and we'll talk in a moment about the effects of the renin-angiotensin-aldosterone system. The effects of enhanced ADH secretion are to cause vasoconstriction and increased water reabsorption by the collecting ducts. The effects of enhanced renin secretion are, through the action of angiotensin II, vasoconstriction, and through the actions of aldosterone, enhanced sodium reabsorption by the collecting ducts. Okay. Please remember that because of enhanced sympathetic nerve activity, there is a markedly diminished filtered load of sodium and avid sodium reabsorption by the proximal tubules. Therefore, there is little sodium that reaches the collecting ducts. What does reach the collecting ducts is avidly reabsorbed because of the effects of aldosterone. Urine sodium excretion will therefore be nearly zero.